In this video, we will return to the situation in our previous problem with the snowboarder, but now we will start introducing the effects of friction, starting with static friction and then moving over to kinetic friction. The question begins as it did last time. A snowboarder begins at rest at the top of a slope, 67.2 meters long, at an angle of 23 degrees to the horizontal, and we will neglect air resistance. Except now, we're going to include static friction, and we ask the question, what would the minimum value be for the coefficient of static friction that would keep her from going down the slope? Well, step one in the process is always to draw a diagram showing all of our information and the forces acting on the object. And that diagram is pretty much unchanged from the previous time with one exception. As before, we draw the incline here with an angle of 23 degrees. As before, she has a velocity of 0 at the top. All right, and if she slides down the slope, she will have a velocity v final at the bottom because she will experience an acceleration down the slope. And we have the length of the slope, 67.2 meters. We include, as before, the normal force, which is perpendicular to the slope, and the weight force, which is always straight down. The exception here is that we now include a friction force. And notice how that friction force is up the slope because the acceleration is going to be down the slope. The friction force always opposes motion. So it is going to be up the slope if the acceleration is going to be down the slope. So that's one change that we make in our diagram. We now include the friction force. Now the second step is to determine a coordinate system, and we do as we did in the previous problem. We change the traditional Cartesian coordinate system. We tilt it because the only real requirement in the Cartesian coordinate system is that x and y are perpendicular to each other. Anything else is possible, but x and y must be perpendicular to each other. So we can take the traditional x and y coordinate system and tilt it so that x is down the slope, which is the direction the snowboarder will travel, and y is perpendicular to the slope. This choice of coordinate system is going to make things easier on us later on because we go to our third step, which is to ask ourselves if any forces need to be broken up into components, and if so, draw those components and come up with formulas. Well, we can see here that with this new coordinate system, it is not going to be necessary to break the normal force up into components because it's purely in the y direction. And there is no need to break the friction force up into components because it is in the negative x direction. The only force we have to break up into components is the weight force, mg. And we can break that up using our new coordinate system into the y component, wy, and the x component, wx. X and y are always perpendicular to each other, so this forms a right triangle. And the angle here in this right triangle is going to be equal to the angle of the slope itself. With that, we can now use the trigonometric functions to find formulas for the x component and the y component, just as we did in the previous example. So that has not changed either. So we have determined that the weight force needs to be broken up into components. We draw those components, and we have used the trigonometric functions to come up with formulas for those components. Now let's see what the inclusion of friction does for us. In this first question, we are asked what's required for her to stand still? Well, now to stand still, that's equilibrium. So the acceleration in the x direction has to equal 0, and the acceleration in the y direction has to equal 0 in order for her to stand still. And so the sum of the forces in the x direction has to be 0, and the sum of the forces in the y direction has to be 0. Wx is one of our forces in the x direction. It is down the slope, so it is going to be positive. The friction force is our other force in the x direction, and because it is up the slope, it is going to be negative. This can only be true if Wx equals the friction force. Now, because we are standing still, we're going to be dealing with the static friction force, which means we have the coefficient of static friction times the normal force. So like in so many situations involving friction, the challenge is now to find the normal force. But we can do that because we know that the acceleration in the y direction is 0. And so the sum of the forces in the y direction has to be 0. And that is the normal force, which is going to be positive, and the y component of the weight force, which is going to be negative. Once again, we have two opposing forces that are in equilibrium, and so they will be equal to each other. And so that means that the normal force equals the weight force times the cosine of 23 degrees. With that in hand, we now swing over to here. The formula for Wx is mg sine 23 degrees. And the formula for the normal force is going to be mg cosine 23 degrees. And this is why I always encourage you to do algebra before you do arithmetic, because you can see that a wonderful thing happens, that mg cancels. And we are left with the coefficient of static friction equals the sine of 23 degrees divided by the cosine of 20 degrees. And we calculate that out to discover that means a coefficient of static friction of 4.24. Notice, no units on the coefficient of static friction. If the coefficient of static friction is less than this, she's going to go down the hill. But if it's this much or more, she will remain stationary. Now our follow-up question is, instead of the coefficient of friction being 0.424, imagine that the coefficient of friction is 0.185. This is kinetic friction because she will be sliding down the slope. So we ask, if the coefficient of kinetic friction is 0.185, what will her new speed be at the bottom of the slope? All right, well now, she is not standing still. And so now, the Newton's second law equation doesn't look like this. It now looks like this. Sum of the forces in the x direction equals mass times acceleration in the x direction. And as we did in our previous example, if we can find this acceleration, we can find her final velocity. All right, well that's going to be, we look back up here at our diagram and we see there are two forces acting in the x direction. Right, so that's going to be Wx minus Fr. Except this time, we're talking about kinetic friction. So now, the force of kinetic friction is mu k times Fn. But one thing that hasn't changed is the normal force is still the same. This normal force that we found up here is still this normal force right here. The normal force is not going to change just because the coefficient of friction changes. It's going to be equal to the y component of the weight force right here. Right, so we wind up with Wx minus mu k Wy equals max. All right. So we use the formulas that we got up here, and we plug them in. Wx is mg sine 23 degrees. Wy, which is equal to our normal force, is mg cosine 23 degrees. And that's going to be equal to mass times the acceleration in the x direction. As in our previous problem, the mass is going to cancel out. The acceleration down the slope is independent of the mass. And when we calculate this all out, g sine 23 minus mu k cosine 23 with a mu k value of 0.185, we arrive at an acceleration down the slope of 2.16 meters per second squared. Now notice that is a smaller acceleration, a much smaller acceleration than we had in the previous problem without friction. Without friction, the acceleration was 3.83 meters per second, but now with some friction, it's 2.16. Well, with that new value for the acceleration in hand, we can go back to the kinematics equation and find her final velocity. The initial velocity is still 0. The acceleration is now 2.16, but the displacement is the same as it's always been, 67.2. That gives us a final velocity of 17.0 meters per second. So her new speed at the bottom of the slope with friction is 17.0 meters per second. Compare that to what we got in the previous problem without friction, 22.7 meters per second, and we see that even a small value of mu k, even a mu k value of 0.185 is still going to cause a significant reduction in the final velocity. But as long as that coefficient of friction is less than 0.424, she will go sliding down the slope.